Okay, we're back with part two here. Still talking about example one. Talking about the domain and range of it. If we just look at the domain and range of the bits that we were putting together, we see that the domain of f is x can't be -3, and the range is y can't be 0. It's got a horizontal asymptote that doesn't touch, and g is very similar except for x can't be -4. So these two, straightforward, actually from grade 11, it's not bad. And for the domain of the combination function, well, what's the domain of the black one? The domain of the black one is the same vertical asymptotes as the other two had. So this is pretty easy. But what's the range here? If we just look at it algebraically, we might be tempted to say that y can't be 0, and indeed we do have a horizontal asymptote, but we also saw in that unit 2 that these functions sometimes, often, go across their horizontal asymptote, and in fact we calculated that where y is equal to 0. Y is equal to 0 at -6.5, right? And so it's not y can't be 0. Is it y is all real numbers then, if it can be 0? Well, no, it looks like there's a little gap in here, right? You see that? It looks like there's a little gap. Don't mess up your note now. But it would be all real numbers except for this little gap in here. But I don't know what that little gap is. I need to find out how far down this function goes and how far up this function goes here. And in fact, I can't tell. I can't tell. So it's not y is all real numbers. There's a little gap. And in fact, without technology, we wouldn't know how to do it. Not till calculus. And the folks not taking calculus with me next semester, well, you'll just have to trust me, I guess. Conclusions. Domain. For x to be in the domain of the sum function or difference function, it must be in the domain of f and the domain of g. In symbols, we would write that the domain, and I'm just going to write DOM, short form, of f plus or minus g is equal to the domain of f, and this symbol means intersection, or also can be read as an and. So this is an intersect symbol. We can also read it as the word and. Domain of f and the domain of g. Well, what about the range? How would we get the range? Well, we said the range is a lot more difficult. My advice is get a sketch, look at the results. You can guess from the graph. Okay. We don't have the skills to calculate the range exactly. Okay. So domain and range, we take the domain of the two separate, and then it has to be in both. So to be in the domain of f plus g, you have to be in the domain of f and in the domain of g. So that means any holes from either of them sort of stick around as holes in the combination function. What do we got? Okay, so this is one of those points ones, and this isn't so bad. Remember, how do we do this? Is the sum function. We just have to go through and find which points in the domain the points are defined for, and then calculate them. Well, notice for x equals -1, we have points in both, so that means it's going to be defined in the sum function. And what do? I just add those two. 2 plus -3 is -1, and if you can't remember where that came from, you might want to put the little calculation over. But notice for the next point, oh, here we go. Actually, we do, right? For x is 1, it's also defined for f, and so I'm just going along the points for f and trying to calculate the combination. So an input of 1 gives me an output of, well, 4 and -2. I'm just adding 4 and -2 is 2. And then I go along, 2. Yeah, it's defined. Both functions are defined for x equals 2, so I can do that one as well. 2 and 0 because that's 3 and minus 3. And I keep going, 5 and minus 2. Well, there's no input of 5 in there, so this point's not, even though it's in the domain of f, it's not in the domain of the sum function because it's not defined for g. So there is no 5, there is no 0, there is no 8, and in fact, that's where my function ends. I do the difference function in the very same way. I know I'm going to have all the same domain values, right? Because it's still going to, the function is still defined for all the ones where it's defined in the two separate functions, but I just combine them in a different way. I do the difference. 2 subtract negative 3 is 5. Right? Be careful with your integers. 2 subtract negative 3, and then 4 subtract negative 2. Watch your integers, that's 6. And then 3 subtract negative 3 is 6 as well. There, done. Easy. Is there another one down here? Yes. Okay, we've got 2 given graphs, and hopefully that's actually in your notes because that's going to be a pain to graph. And this is the very same thing as we did with the example 1, right? I can't calculate the black function, the sum function algebraically, so I have to do it graphically. And getting ahead of myself here. One thing I want to point out is, where is my combination graph? I'm going to do this one in blue. Where is it going to exist? Well, it's only going to, these combination functions are only going to exist where both functions are defined. So you see this bit, we just ignore it because f isn't defined there. Okay, dandy. Now how do I do this? Well, I'm going to use green for that one, red for this one, Christmas colors, right? F plus G, F plus G, and then there is my point on this. This is going to be the sum function. So this one's going to be F plus G. I just added the 2. Oh, no, I goofed, didn't I? Because this should be 4. Did you copy that down? Oh, boy. Sorry about that. Don't mess up your notes. I forgot it's a minus, right? So this is f minus 2, f plus negative 2, and the sum function is right there, right? And similarly, I'm going to skip to the next nice point. I got green plus red. That's a minus. Green plus red is right around there somewhere. And I keep doing this. Green plus red is going to be here. And I'm just doing a few. Green plus red. Those are about even, right? You see that? Green and red are about opposite, so it's like this. Green plus red. I'm going to show you that one too. Green plus red. Green plus red is going to be down in the negatives, right? 2 and minus 4 is minus 2. And this function here, some sort of curve it looks like, is f plus g. Okay, and then I want to do f minus g. F minus g. So green, aha, see, this is what I was starting to do originally. Green minus negative 2. Green minus negative 2 is adding 2. It's going to be, the first point's going to be up there. Green minus 1 and a bit. It's going to be here maybe. 3 minus negative 2 is 5 there. Then I have 2 and a bit minus negative 2 and a bit is 5 again. 2 minus negative 4 is 6, and I get that function. This is f minus g. So, okay, let's just skip the last one because it's the same. Well, No, it's not the same. So I'm going to use pink. Why not? And dots. It's not the same, right? Because this time it's G minus F. So let me show you that. And I'm going to start off on the left here. Red minus green. So -2 minus -4 is way down here. Where's my pink there? Pink. What was it? It was 2 minus 4 is -6, right around there somewhere. And then I keep doing this, right? I've got my -1 and a bit, minus another 3 and a bit is way down here somewhere. 2 minus, or -2 minus 3, and I'm just doing this graphically now. 2 and a bit, -2 and a bit, and then finish it off here. -4, subtract 2 is another. These are not the same, are they? This is going to be weird when I write it. Oh well. That's, oops. I'm going to write it normal. G minus F. You notice something? Well, first of all, these two things are not equal. Not equal. Do you see what they are, though? If I think of this axis, they're flips of each other, right? They are flip. Well, I flip it right over this axis, and I'm going to get this pink one. And in fact, I could write that. F minus G equals the flip vertically of G minus F. And if you work out the algebra, that works as well. All right, Dandy, do we got one more? We do have one more. How's my time doing? I think we have, yes, we're going to have to come back for the dreaded video 3. Dun, dun, dun.